Hi everyone, my name is Yukiko Sawaya, and today I'll present our work on a high coverage cybersecurity scale predictive of user behavior. This is a joint work with my collaborators from KDDI Research, MIT, and Tel Aviv University. Psychometric scale captures user security and privacy attitude and behaviors through self-reports. Among others, they can be useful for accommodating users' preference, raise privacy awareness, and measures changes over time. However, a significant challenge is the low correlation between these scales and actual behaviors. In other words, there is often little connection between what users say and how they behave. The Security Behavior Intention Scale, or CBIS, is a de facto standard for measuring security behaviors and intentions. It consists of 4 subscales: device securement, proactive awareness, updates, and password. These subscales are assessed through 16-item questions. CBIS items are based on 30 initial security advice recommendations. Sourced from US ISPs, USENIX, and industry consortia. So in our work, we hypothesized that the omission of critical factors that may directly impact users' security behavior can harm the scale's ability to predict actual behavior. So in other words, we expect that the scale covering a more comprehensive set of security-related factors can predict users' behavior more accurately. To test this, we developed the Extended Security Behavior Scale, ESBS, which covers a wider range of items and factors than CBIS. Then we compared prediction accuracy of security behaviors with past instruments that have less coverage. Our approach is divided into 3 steps. For the scale development, initial items were selected from a large advice pool, and an online study refined the items using exploratory factor analysis to create the scale. Then another online study was conducted to assess the scale's reliability and validity. High reliability indicates consistent measurement of the same construct, while high validity confirms the construct holds across independent samples. For the last step, online study tested prediction accuracy of actual behavior with ESBS and CBIS using machine learning models. Our study protocols were reviewed and approved by RRB of Tel Aviv University. We first developed the security behavior scale inspired by CBIS, starting with a comprehensive set of 374 security advice items identified by Redmond et al. To create a practical questionnaire, we applied criteria such as utility, priority, and applicability, narrowing down to 45 items. These items were rephrased into statements with responses on a 5-point Likert scale with a non-applicable option. Then we conducted an online study to refine the scale and identify subscales. We recruited roughly 300 US participants via Prolific, ensuring a representative sample. Then exploratory factor analysis was applied for creating the scale, which is typically used for assess correlations between statements and identify the structure of underlying latent construct, that is, subscales, behind the main concept. So EFA identified 5 subscales data securement, proactive awareness, antiviruses, updates, and passwords, which are composed of 20 items. Besides the standard 5-level Likert scale response options, we also allowed non-applicable response options. We mapped non-applicable responses to never, because if a respondent answered no applicable, then they never follow the corresponding behavior. So here we compared the ESBS with the CBs. Our scale is composed of 25% more subscales and items, which included 30 unique items not covered by CBs. These additional items encompass critical security behaviors such as encryption, multi-factor authentication, showing ESBS offered a broader scope of user security behaviors. 13 of 16 items of CBs were covered in ESBS. The remaining 3 items were excluded due to seeding effects or low correlation with main factors. For the next step, scale validation, we validated the ESBS by conducting a study where new participants responded to the ESBS questions. We recruited 500 US participants via Prolific, ensuring a representative sample. We validated the reliability of overall ESBS and subscales and confirmed the structural validity of the scale. The scale's reliability and structural validity were assessed using Cronbach's alpha and various goodness of fit measures. All metrics fell within the recommended ranges, confirming that the ESBS and its subscales are reliable and validly structured. For the behavior prediction, we conducted 2 studies focusing on browsing behaviors and operating system updates. We focused on 2 behaviors for browsing and 1 behavior for operating system updates. In the interest of time, we will only present the result related to browsing behavior. We recruited over 200 participants for the study of browsing behavior through Prolific. Considering the sensitivity of the browsing data we collected, we increased the compensation compared to the previous studies. We designed a study to gather responses on ESBS and CBs and collect browsing data by asking users to fill out questionnaires and use a Chrome extension we developed for the study. We then built a machine learning model to predict whether users compartmentalize browsers or clear browsing history based on ESBS, CBs responses, and demographics. We tested the model's accuracy via area under the curve of receiver operating characteristics and compared the accuracy of models trained on CBs and ESBS via t-test. So here are the results. Each box shows the condition of the combination of independent variables. In summary, ESBS achieved a 13% increase in accuracy for browsing session compartmentalization compared with CBs. For clearing browsing history, ESBS showed a 7% improvement over CBs. So our scale also predicted operating system updates behavior more accurately. Overall, ESBS outperformed CBs in predicting security behaviors. So some limitations should be taken into account when interpreting our findings. First, a participant or younger educated US individuals form prolific. More recent work we have, however, shows a generalization of some results to other populations. Second, the ESBS predicted 3 specific behaviors better than CBIS. Still, its effectiveness on a broader range, especially on mobile and cloud platform, remains untested. Thus, random forest performed best among evaluated models, yet other models may outperform them. So then we discuss how our scale may be applied in the wild. For researchers, ESBS can be employed as a cost-effective and non-invasive tool to study such as user behaviors, variations across cultures or over time. For practitioners, ESBS predictive power can be exploited to implement effective personalized interventions. While individual subscales might be more predictive for specific behaviors, using the full scale is recommended since we found that using them all together maximizes prediction accuracy. So ESBS has more items and requires slightly more time to answer than CBIS, but it achieves higher predictive accuracy, especially in settings where accuracy is critical. So in conclusion, we developed the ESBS, a high coverage scale spanning various security-related factors. It has higher coverage than prior scales. It's reliable and maintains structural validity and is high predictive of 3 different behaviors. So please consider reading our paper for more details. Thank you for your attention.
Thank you.